Hello friends, welcome to engineering tutorial. In my previous 2 or 3 videos, I discussed some of the concepts related to amplitude modulation, such as formation of an amplitude modulated signal waveform, modulation index, sidebands and power relationship, which are related to amplitude modulation. So in today's video, we are going to start a new concept related to modulation, or a new category of modulation, which is called as angle modulation. So what is angle modulation? So obviously it involves the change of the phase angle, which involves both frequency and phase of a carrier signal with respect to the instantaneous value of the modulating or message signal, while the amplitude of the carrier signal, it remains constant. So there is no change in the amplitude, but only the frequency and the phase angle of the carrier signal are changed or altered or modulated in accordance to that of the characteristics of the message signal. Angle modulation is of two types. It is divided into two categories. First is the frequency modulation, second is the phase modulation. So angle modulation is of two types. Frequency modulation, in which the frequency of the carrier signal, or the instantaneous frequency actually of the carrier signal, is changed proportional to the message signal, and phase modulation, in which the phase angle of the carrier signal is changed with respect to the message signal. Here the initial phase remains unchanged in frequency modulation. In phase modulation, the frequency remains unchanged. So we will discuss these two modulation techniques separately. In today's video, we are going to discuss some of the concepts related to frequency modulation. Okay, so let's go in detail about it. So let us discuss some of the mathematical details which are related to angle modulation. So what are we going to basically do in angle modulation when we change the instantaneous angular frequency or the phase angle? Let us say the unmodulated carrier signal, which is to be modulated, be given by this expression. The carrier signal as a function of t is equal to EC cos omega ct plus phi 0. Here EC is the amplitude of the carrier signal, omega subscript c is the angular frequency of the carrier signal, and phi 0 is the initial phase of the carrier signal. This part is written as psi t, EC cos psi t, where omega ct plus phi 0 is equal to psi t. This carrier signal wave has to be modulated proportional to the message signal, where the frequency or the phase angle is changed. In angle modulation, these two parameters are involved, the angular frequency and the phase angle. So this phase angle of the carrier wave, which is psi t, the total phase angle, is given by omega ct plus phi 0. So when we differentiate psi t with respect to time, we get the carrier frequency. This is actually the instantaneous frequency. Okay, so when we differentiate the total phase angle of the carrier signal, we get the instantaneous frequency. Always remember, this is a very important relationship in reference to angle modulation. Here try to understand. Here we have represented the total, this total value omega ct plus phi 0 as psi t. So when you differentiate psi t with respect to t, we get the instantaneous frequency. Here the instantaneous frequency, in case of this signal, the instantaneous frequency value is equal to the carrier frequency of the signal, the carrier wave. But in general, we write this as the differentiation of the total phase angle of the carrier wave with respect to time gives us the instantaneous frequency omega subscript I as a function of t. So if you want to calculate the total phase angle, you just simply integrate the instantaneous frequency value with respect to t. Okay, you can pause the video and note down these things and just go over them so that you can understand it in a better way. Okay, so this is the main relationship. Actually, these two are the main relationships which are involved in angle modulation, be it frequency modulation or phase modulation. Okay, next is frequency modulation. So frequency modulation, it is the modulation technique in which the frequency of the carrier signal, actually the instantaneous frequency which I discussed previously of the carrier signal, is changed with respect to the message, modulating or baseband signal. These three things are the same. Again, never ever get confused between message, modulating and baseband signal, they are the same. And the amplitude of the carrier signal remains constant. Only the instantaneous frequency of the carrier signal, which is omega subscript I, which I discussed previously, is altered with respect to the message signal. How it gets altered, we will discuss it here. Again, let us consider the unmodulated carrier signal wave as EC cos omega ct, which we have taken. But here the interesting thing is that for the sake of simplicity of calculation, we have taken the initial phase phi subscript O as 0. This is just so that the calculations do not become complicated, for easier understanding and analysis. Now, here, as I said, we have to change the instantaneous frequency of the carrier signal, okay, proportional to the message signal. That can be written as omega c plus kf mt. Here the initial unmodulated signal wave had frequency omega c. So now this parameter kf mt, this is the extra thing which gets added. This whole process, this whole expression represents frequency modulation. Omega subscript c was the frequency of the unmodulated carrier wave. When this parameter kf into mt gets added to it, frequency modulation is achieved, and this whole value is called as the instantaneous frequency, which is time varying, which is a function of time. This whole expression is actually what constitutes frequency modulation. Kf is the frequency sensitive component or the proportionality factor. So now when you have to calculate the instantaneous phase angle, which is psi subscript I t, we have to integrate the instantaneous angular frequency with respect to t, which I discussed in the previous paper about the integration. We have to calculate the phase angle as the integration of the instantaneous angular frequency. So now when we integrate it, we get the value as omega ct plus kf integration of mt dt. Never ever write that you directly put this expression in the carrier wave. You have to integrate it. Never put it directly. That will become phase modulation. Here the instantaneous frequency gets modulated. So we have to first define the instantaneous angular frequency. Here the instantaneous angular frequency is this much, omega c plus kf mt. Omega c is the frequency of the unmodulated carrier wave. This parameter kfmt gets added to it, so we get the time varying instantaneous angular frequency. So in order to calculate the total phase angle or the instantaneous time varying phase angle, we integrate this value with respect to t, which we get as omega ct plus kf integration of mt dt. So now the frequency modulated carrier wave is given by E subscript fmt is equal to ec cos psi subscript I t, which is given by ec cos omega ct plus kf into integration of mt dt. Again, please pause the video and note down these expressions in your copy so that you can understand them in a better way later on. So this is the mathematical expression for a frequency modulated carrier wave. Okay, always note down this thing, always take special care of this thing, the instantaneous angular frequency and the time varying instantaneous phase angle of the wave. These two are very important in angle modulation, be it frequency modulation or phase modulation. Okay, so this is the mathematical expression of the frequency modulated carrier wave. Next, so in frequency modulation, the carrier frequency changes in the following ways. Now, during the positive cycle of the message signal or the modulating signal or the baseband signal, there is compression which occurs in the carrier signal wave. Positive cycle of the message signal, compression in the carrier wave. And during the negative cycle of the message signal or the modulating signal, there is expansion in the carrier signal wave. These two things are very important. During positive half cycle of the message signal, there is compression in the carrier signal. During the negative half cycle of the message signal, there is expansion in the carrier signal. Let us see how it happens. See here. Here we have the message signal or the modulating signal or the baseband signal. This is the carrier signal which is to be modulated. As I said, the message signal is of low frequency, the carrier signal is of high frequency. Hence, the message signal has low energy content and the carrier signal has high energy content. Now, as we discussed, during the positive cycle of the message signal, there is compression in the carrier signal of the frequency modulated wave. So here, during the positive half cycle, there is compression in the frequency modulated wave during the positive half cycle. During the negative cycle, there is expansion, which is marked by a slightly lower frequency. Again, during the positive cycle, there is compression, which is marked by an increase in frequency of the wave, of the frequency modulated wave. Again, during the negative half cycle, we have expansion, which is marked by a slight decrease in frequency or increase in time period of the wave. Again, during the positive half cycle, we have compression in the frequency modulated wave, which is marked by increase in frequency, and during the negative cycle, we have expansion in the frequency modulated signal, which is marked by a decrease in the wave. Actually, this changes occur in the carrier signal, which leads to the formation of the frequency modulated signal in this way. Now, my drawing skills are not that great, so that's why you might find it a little ugly, but still try to understand. Compression means the frequency is high and expansion is marked by a slight increase in time period of the signal, which leads to decrease in the frequency. So if you can just visualize the difference, it will be very great. So this is what a frequency modulated wave looks like. So here we have discussed some of the basic concepts related to formation of a frequency modulated signal, how the instantaneous angular frequency is altered proportional to the message signal, and how we calculate the total phase angle by integrating the instantaneous angular frequency with respect to time. So in my next video I will be discussing other concepts related to frequency modulation, such as frequency deviation, the modulation index, and the bandwidth of a frequency modulated wave. So please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, communication and instrumentation engineering. Have a great day. Thank you very much.